You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Brian Keating. Dr. Keating is a physics professor at the University of California, San Diego, and the director of the Simmons Observatory, specializing in the study of gravitational waves created during the early stages of the Big Bang. Dr. Keating is also a pilot and is the recipient of the 2007 Early Career Award for scientists and engineers for his work with BICEP.
Dr. Brian Keating, welcome back to the program.
John, it's great to be with you. I think it's been more than a year. I've been going through JMG withdrawal.
JMG withdrawal. I never have to go through that because I'm constantly him. Brian, tell me about the Simons Observatory and your current work.
Well, this is perhaps the conversation I've been waiting to have with you in the 6 years we've known each other or so. And that's, we finally got data with the Simons Observatory, which is the most ambitious, most expensive, most expansive experiment in my field of cosmology. And it really couldn't have come at a better time, for me personally. Scientists are people, John, and we get the reputation for being passionless robots that are just walking Wikipedias, but we have emotions. And just recently, my father figure in my life, Jim Simons, passed away. And he, of course, not only did he fund the Simons Observatory and the Simons Array, but he was, like a father figure to me in many ways. I've known him since before I was born. He hired my father to teach mathematics at the State University of New York at Stony Brook, where I was born. And they knew each other and worked well together for many decades. And then later on, he decided he had a passion for philanthropy and science and cosmology in particular. And he asked me, well, what would it cost to build an observatory that would take us back to the very beginning of time, hoping to resolve the question of whether or not the universe did begin with a Big Bang or not. And what was the nature of that Big Bang? Or was the universe cyclical? Or was it a one-off? And all these mesmerizing questions. He was probably one of the biggest thinkers I've ever known. Incredible scientist, billionaire, brilliant hedge fund manager, and then a philanthropist. And to have, to be the number one in one field is hard enough. To be the number one in three different fields is just unheard of. So he's a remarkable individual. I promised him when he funded this observatory, it's a $110 million observatory, that he would see the first results before his 86th birthday, which is in April 2024. And by golly, thanks to my incredible team members and my colleagues and fellow leaders of the project, we got it done. And we showed it to him on his 86th birthday. He saw the first results. And, sadly, tragically for me personally and many around the world, he passed away, 3 weeks later. So it really couldn't have come at a better time. And we are more excited, more motivated than ever. We just had a face-to-face meeting with nearly 250 of the most brilliant scientists on Earth gathering together at the University of Chicago, and had a meeting to present our current results, embargoed results and results I can't talk about or show you necessarily just yet or put on my, platforms. But it's just breathtaking. The quality of data, the sensitivity that we're reaching, the data processing that we're employing, the supercomputer power we're throwing at, managing this vast amount of data, a terabyte a day. Which a particle physicist will laugh at. But, John, those guys and gals get, one event every month or something. Yeah, they have a petabyte a second or whatever, but they throw out, 99.999, 10 to the 15th of every data point they keep, one out of every 10 to the 15th. So we're in a different noise signal regime. We're observing the cosmos. We're seeing objects. We're getting just stunning quality data, and it's only just begun. And it's going to get better and better every day, every month, every year for the next nearly a decade. We're funded for the next decade, and there's really no one else in sight. Our closest competitor is many years behind us, potentially, if they get approval. They were recently dealt a huge setback. This is the CMB Stage 4 experiment, which is not really a competitor. I mean, we're very close colleagues and friends with all of them, and we hope that they proceed such that someday we might even merge with them. But, they were really set to be the dominant observatory, the definitive, the final CMB observatory. And then the NSF made this knuckleheaded decision to basically halt science at the South Pole, where I've been twice, It's one of the premier places to do science, and that includes the CMB Stage 4 project. So right now it's literally on ice, leaving the Simons Observatory, thanks to Jim Simons' vision, poised to be perhaps one of the last and greatest of all the CMB cosmic microwave background observatories.
Now, what's the equipment look like, the detectors?
Well, we have 4 massive telescopes, one that's truly massive with 6-meter diameter, 2 6-meter diameter mirrors, more than 20 feet across, bigger than the James Webb Space Telescope mirrors, dwarfs the Hubble Space Telescope. We have 2 of those embedded in a single telescope, which we creatively call the Large Aperture Telescope. And that's a reflecting mirror-based telescope. And then we have 3 refractor telescopes that use lenses that are, almost a half a meter in diameter. So larger than almost really the largest refracting telescopes ever built. The optical versions of those that you could look through at Yerkes, they don't make them anymore because they're too difficult and painstaking to build. So this one in Yerkes is about 100 years old, and it's 40 inches. It's a little bit about twice the diameter of our telescope. But nevertheless, our aperture we have 3 of these devices, and they're cooled down to nearly absolute zero. They're literally the coldest telescopes in the known universe. As far as we can tell, they're cooled down to 60 milledegrees Kelvin. So 0.06 Kelvin. It's stunningly, staggeringly incredible technology called dilution refrigerators. And those were designed and built by my colleague who's now a professor. He's my former postdoc here at UC San Diego, Dr. Nick Galitsky, who's a professor now at UT Austin. Shout out to the Longhorns. And he designed and built most of those when he was here, the design for them. And then we built one of them. My colleagues at UC Berkeley built another telescope version of it, exact same optics and so forth, just different frequency detectors. And then the same as ours was built at Princeton by my good friend and colleague, Lyman Page, who's a great contact that you should have on to talk about his great book called The Little Book of Cosmology someday. And these 3 are refracting telescopes. So the refracting telescopes are meant to look for the aftershocks of inflation. If inflation took place, the universe should be suffused with a gas of gravitational radiation, percolating and permeating the cosmos, disturbing the gravitational force field of you and me by an imperceptible amount to us. But as the universe was much more dense and compact in the past, the energy of these gravitational waves was trillions of times higher. And in fact, if we look at the density of gravitational radiation, if inflation took place, at a time when the cosmic microwave background, the very first atoms formed 380,000 years after the Big Bang, so talking 13.8 billion years ago, the universe was 1,000 times more compact than it is now, which means its density was 1,000 cubed or 1 billion times more dense than it is now. And the density of radiation energy in the form of gravitational waves was 1 trillion times larger than it is today. So we're using the early universe, the photosphere that we call the cosmic microwave background. We're using that as our detector. That's really our detector. So you asked how cold is our detector? Well, that's the 3 Kelvin background. Of course, the detectors that my colleague Suzanne Staggs builds at Princeton University operate at 60 millikelvin in the receiver on Earth in Chile at 17,200 feet above sea level. We're the highest cosmological observatory and really the second highest observatory of any kind on Earth. And our colleagues at the Tokyo Astronomical Observatory are about 1,000 feet higher than us, but they're doing a completely different type of science. So these instruments have never really been deployed in this massive number. We're talking 60,000 detectors at a time. And we hope to have, first data that's science quality after we calibrate, after we remove certain noise features and understand the instrument better and better every single day. We hope to have results in the next year or so.
I do not envy noise, so I guess noise is the reason you have to cool those telescopes down so much, right?
It's one of the reasons. Yeah. There's 2 different types of noise. There's noise that can be reduced by taking more and more measurements. So if you want to measure the width of the desk where you're sitting right now, you can do it multiple times, or you could have multiple people do it. And that type of measurement error is statistical in nature. It will improve every time you measure it. It won't get better by the number of measurements. It only improves by the square root of the number of measurements. For us, that means if you want to double your sensitivity purely by increasing time, you have to measure for 4 times the amount of time. So if you want to double the sensitivity, all things being equal, you have to observe 4 times longer. Then there are sources of noise that you can't get rid of by making more measurements. Every time you measure them, you get the same result, and it's still the incorrect result because it's this thing they're trying to measure plus something added by the system, and those are called systematic errors. And examples of those could be a local contamination from the ground. Remember, our detectors are trying to see, they're cooled to 60 millikelvin. They're trying to see a signal that's a few nanokelvin, and they're sitting on Chile's, mountaintop that's 300 Kelvin. So you're talking, something like, thousands and, a billion times hotter temperature that surrounds us. That you can't get rid of but by taking more and more measurements. What you have to do is do specific measurements that are not parallel to your scientific goal. So we're trying to measure waves of gravity percolating through the cosmos, imprinting the cosmic microwave background's polarization with a characteristic pattern called B mode or curl mode polarization. That pattern is also produced, or a pattern can be produced just like it, by our galactic magnetic field and the dust that exists within our galaxy. In fact, that was the undoing of the BICEP 2 result that I played a big role in and also was the subject of my first book, Losing the Nobel Prize. We saw an astronomical signal with exquisite sensitivity that was incredibly hard to do. That instrument was based at the South Pole, based on a design I came up with when I was a postdoc 20 years ago at Caltech. That telescope made an exquisitely precise measurement of a signal that we exactly thought mimicked the imprint of gravitational waves, but it turned out to be caused by dust in our galaxy. So imagine going through all this work, making an honest-to-goodness, incredibly high significance signal-to-noise measurement of an astronomical quantity, but it wasn't something that was cosmological. It told us about our galaxy, but it told us nothing about whether the Big Bang was singular, whether there are multiple Big Bangs, etc. So that was, of course, a great embarrassment, as I talk about in that memoir, Losing the Nobel Prize. So that's another systematic error. You can't get rid of that by just making more measurements. You have to make a dedicated measurement to the systematic effect and throw that data away in terms of its cosmology content. You have to do a measurement to basically measure the amount of dust. And I analogize it to, let's say you're driving at night and your windshield is covered in dust and whatnot. So a simple thing you can do is just squirt that blue juice that comes out of your car windshield wiper fluid tank, and then the windshield wipers will remove it. So you did an experiment. You actually looked not at the road ahead. You were looking at just the windshield, detecting an unwanted impersonator, in this case, the dust on the windshield, and then going through an experiment to remove it, and hopefully that removes it and it's gone. Well, we can't go out into the galaxy and squirt some windshield wiper fluid everywhere to get rid of the galactic dust, thermal dust emission. So we have to go and build an experiment dedicated just to measuring dust. Then we combine the dust only measurement with the cosmology plus dust measurement. We subtract the dust only from the cosmology plus dust, and what's left is the cosmology signal. So that's a long-winded way of answering the question of what we're actually measuring in terms of our noise. That's what we get paid for. We don't get paid to necessarily measure the signal. A good scientist spends most of their time trying to measure the noise.
And thus getting a quality data set, and then from there you can do something. Now, this telescope, now where is it located? This array, actually, where is it located? Is it in Chile or?
Yeah, so it's in the Atacama Desert of northern Chile, which is about a 2-hour flight from Santiago, which is the capital, and most of the population lives in Santiago. And the observatory is located on the high desert. It's really some of the highest mountains in the world, in the Andes Mountains. They're stable, but they're actually volcanoes, and some of them are still active. It's not far from the ALMA Observatory, which is the most expensive astronomical observatory ever built, which is a radio observatory doing very different type of science, but looking at things like exoplanets and molecules and molecular astronomy and things like that, and extragalactic astronomy too. But we're sort of unique right now in that we're looking for this incredibly faint signal that, if truly detected and not like dust like last time, would be a Nobel Prize winning discovery. Everybody knows that.
And that brings us to another almost certain Nobel Prize. which would be the discovery of the axion, the mythical axion. Tell us how you can do that with this observatory.
So it's very interesting that cosmology is now intruding upon the territory once only trodden by particle physicists. Namely, we are looking for the properties of particles, not using CERN, not using SLAC, not using any earthbound terrestrial or even solar system-based detector. We're using the whole cosmos as a particle accelerator. And in fact, we're using the Big Bang itself to test the theories of particle generation. And there are many mysteries in our universe, as you are well aware. One of the biggest ones is, what is most of the matter in the universe made of? We know that the matter that you and I are made of, the protons, the neutrons, and my favorite particle, the crouton, they're all made of ordinary stuff. We call that baryonic matter. It just means heavy matter, matter that's made of massive objects, in this case quarks or electrons, which are called leptons. But we also know that there must be dark matter in the universe. This comes about from the work of Fritz Zwicky in the 1930s, looking at the Coma cluster and their high velocity of these galaxies that are moving too high to be whirling about without some additional unseen, non-luminous form of matter that was pulling them and tugging them and giving them this incredible velocity. It's later independently verified by Vera Rubin, looking at galaxies and their rotation curves, and seeing that the rotation of the outermost stars in our galaxy and every other galaxy she could measure were going way too fast to be constrained by the matter that she could see with luminous optical telescopes. So the presence of dark matter has been known, and it's verified as a necessity for the last 7 decades. But we don't know what it is. We don't know what that dark matter is, or if it really is a new particle. We tend to have a bias in most of physics that it must be a new particle. And there's a good reason for that. I'll get back to that in a second. But there are many people, including a friend of mine, past guest and professor at my alma mater, Case Western, Stacy McGaw, and Mordecai Milgram, who I've had on the Into the Impossible podcast, who's the originator of a theory called MOND, which proposes that no, there's no new missing matter, unseen particles. Instead, you have to modify not Einstein's theory of relativity, but Newton's theory of gravity, of universal gravitational law. And in fact, you have to modify F equals ma, which is, Newton's second law. So these are very, very controversial conjectures, but as a scientist, you need to be open-minded and not be biased that you know the answer before you go out and do the measurement. So let's leave MOND aside for a moment, because we actually have detected dark matter. And that is, we've detected the presence of neutrinos. And we know for a fact that neutrinos interact only via the weak nuclear force and the force of gravity. They have a measurable mass, although we don't know exactly what that mass is. And they have no interactions with other known forces other than the weak nuclear force. So they're what are called WIMPs, weakly interacting massive particles. But there's a problem. There aren't enough neutrinos and they're not massive enough. I said we know their mass can't be bigger than a certain value. That's called an upper limit. And it also can't be smaller than a certain value. That's called the lower limit. But we have an upper limit and a lower limit. That's like saying you're greater than 0 pounds, but you're less than 1,000 pounds. It's true and it's accurate, but it's not precise. What we want to do as physicists is measure with precision equal to what a particle physicist would do, and measure the mass of the neutrino to equivalent precision levels. We will be able to do that with the Simons Observatory. That's down the road. That's one of our main science goals, in addition to the measurement of gravitational radiation from the Big Bang's inflationary epoch. If inflation took place, which we don't know for sure is the case, again, we must be open-minded. We must be open to the fact that inflation didn't occur and analyze the consequences and the impact and resulting data set that would emerge. But leaving that aside, we have reasons and a lot of circumstantial evidence for inflation. And we have knowledge of WIMPs that exist, weakly interacting massive particles. And we know certain other types of dark matter can exist, called machos, or like little Jupiters floating around in our galactic halo, or primordial black holes floating around out there. We've put stringent limits on those. Those are called machos, or massively compact halo objects. We've eliminated those as really a candidate for dark matter. So what's left are other types of non-baryonic. They're baryonic, they'll interact with light. That's a no-no. There are other types of particles conjectured to exist, which would interact via the weak nuclear force, in some cases via the strong nuclear force, but not through electromagnetism. They're basically like some heavy forms of photons. Imagine if you could have a photon that had mass and it only interacted via the weak nuclear force. So it's not a photon, you couldn't see it, but that's the analogy we give. And then the question is, well, what properties would these objects have? And they have several different properties. One, and they're called axions, the most leading promising candidate, according to many of my theoretical colleagues. And I'm not biased towards any of them. My job is to disprove all of them, to be honest with you, John. I get more fun disproving people than proving people right.
Experimentalism.
That's right. That's my job. People think, well, what do you hope will happen? I hope, I don't hope for anything. I go where you're going to actually make a discovery, and that will be of interest to me, and I want to do the best possible job. And so these axions will leave many different signatures, but two of them are kind of easy to visualize. One is that because they're a form of dark matter, they'll contribute to the formation of galaxies and clusters of galaxies. And there's some problems with galaxy simulations in that they predict kind of an overabundance of galaxies that are really, really, really small. Sort of like a power law. Like there's many, many more very small insects on Earth and bacteria by mass than elephants, right? So the total land mass of a type of Antarctic krill is the dominant form of life on Earth by mass. And it's very small. You can't see it with your eye. And then on the other side are elephants and blue whales, and there's very few of those, and they don't contribute very much to the mass of the Earth's biomass by a long shot. And so those are two ways of kind of solving the dark matter problem. You can have abundance of small things, or you can have very, very few really large things. So the axions kind of play this magical role. They're very light, but they're massive. They're not zero mass. So if they're zero mass, it doesn't do anything. But there's so many of them that their sheer numbers caused a lot of these problems to be alleviated. The galaxy's small clumping problems. And in the context of what I study, they would make an imprint on the cosmic microwave background's polarization. They would induce an effect, several different types of effects. But the most pertinent one is that if you think of the polarized glasses that you wear to the beach, their job is to filter out one of the two linear polarization states of light. Now imagine you're at the beach and you're staring at the ocean. There's a glare, but your sunglasses are blocking out the light. Half of it, they're blocking out the half that gets polarized by reflection from the water's surface. But then imagine that someone was sloshing the ocean back and forth and rotating the horizontal plane back and forth by some amplitude. Well, then your glasses wouldn't work so well, and you'd kind of get annoyed because every now and then, periodically, your eyes would let in and see this tremendous solar glare, and that would really bug you. And so sort of what would happen with these axions is that they induce a rotation of the plane of polarization of light. And we can see that, even though it's a tiny effect, we with our telescopes can see it over vast cosmic distance scales, because even it may be a tiny effect by these tiny axions, they have enough of them over the cosmological history of the universe. That's a very long path that these photons have traveled since the Big Bang. And that allows us to amplify effectively a tiny signal into an observable signal. In March, we published a paper looking at the oldest continuously monitored supernova remnant. It's called the Crab Nebula, and it's in the constellation Taurus, sometimes called Tau A or Taurus A. It's a radio frequency beacon. It's very bright. There is a pulsar in its center. We don't see the pulsar in the microwave region that we look at, but people have observed it in milliseconds, a few hundred millisecond long pulsar at the center, which is like a neutron star that's wobbling back and forth and beaming out waves of radio emission and towards different distant observers in the universe. And we can actually see that. Those were discovered by one of my favorite past guests, Jocelyn Bell Burnell, back in the 70s when she was a grad student, and she mistakenly thought for a few minutes that they might be the signatures of an alien civilization. But we're not going to talk about aliens today because that really gets people riled up. Getting back to the Crab Nebula, in March, we published a paper that seemed to suggest that there's some strange behavior never before seen in the Crab Nebula, that this supernova remnant's polarization is wobbly. It's not constant. It's not at all related to the pulsar. It's on 2-month-long timescales that the amplitude and is modulating. The angle of rotation of the polarization is changing every 2 months in a sinusoidal-like fashion. We have no idea why that's happening. Could be intrinsic to the pulsar or to the Crab Nebula or to our local environment. We have a 25-page paper of which, as I told you before, probably 20 pages are dedicated to understanding the errors and how we could be wrong, not right. We go through that in painstaking, excruciating detail. This is led by Kiyohei Yamada, who's now a postdoc at Princeton University, just a brilliant scientist, and our whole team. And we're left with one possibility, although it's the least likely in my mind, but it's still fun to think about, that this signal could be caused by axions, that they could be leading to a signal which would induce a modulation of about the amplitude that we see, about the frequency or period that we see, and it's not been ruled out. We're the first to see it. We're immediately conducting a follow-up. This was done by the Polar Bear Telescope, which is not only a precursor to the Simons Observatory, it's a precursor to the precursor to the Simons Observatory. It's about the same epoch and legacy as BICEP 2. So we built this telescope in 2011 to test out the site and to observe the CMB B-mode polarization and look for gravitational waves and look for inflation. But along the way, we've discovered that it was good for doing many other things, one of which is to constrain or possibly detect the presence of axions as dark matter candidates. So this has been one of the most tremendously exciting, but also nerve-wracking and terrifying. And it really reminds me of exactly what happened 10 years ago with BICEP 2, that, we have this huge discovery, but unlike what we did with BICEP, we immediately shared it with critics, with our competitors, who gave us their unvarnished, they actually went through and reanalyzed our data. And so we got a gut check from our scientific competitors. And that was something we never did with BICEP, much to my regret. And I think it led to me having a lot better sleep these last 6 months, because knowing that these eminent scientists couldn't find anything wrong with it. We also peer reviewed it, and it was published in Physical Review, which is the preeminent journal in all of physics. Unlike BICEP, we published after the press conference that announced the discovery of inflation. And so a lot of things are conspiring. Now, it took a lot longer to do all this. All these checks are very painstaking. They take a lot of time. And guess what? Our competitors, they could see this too. If this is real signal, our competitors that we shared this with, they're looking for it right now in their data. And that's a risk that we take. But to have the confidence in a discovery that could be once in a lifetime is kind of offset in terms of scientific ethics. We must do it, in my opinion. And we should have done it in the past.
Looking for cosmic inflation. Now, we've touched on it briefly, but I want to go on a deep dive. The idea of inflation, what is that circumstantial evidence that led scientists to suspect that this inflationary period existed, and I guess to an extent still continues? What led to that? Because it is somewhat of an extraordinary claim when it first started.
Yeah, you're right. The inflationary paradigm was a Hail Mary thrown by Alan Guth back in 1979. He was a postdoc, which is kind of this purgatory position between being a graduate student and maybe being a professor, maybe getting a tenure track job. He had a kid, I think, was living at Stanford and working at the Stanford Linear Accelerator Collider, which is called SLAC. And he, one night, was musing about certain problems that he had heard from the famous Robert Dicke, who's one of the greatest physicists of the 20th century. And Dicke had this idea that it was peculiar that we lived in a universe that was the way that it appeared to be even in the 1970s, which is to say the universe had a certain amount of matter, and that matter was very close to the value that cosmologists call flat curvature, zero curvature. In cosmology, your density is your destiny, and the amount of energy density in the form of radiation matter and some other unseen matter or energy that he didn't know about it was very close to this parameter called omega equals 1, which meant that the density of our actual universe divided by the density of the so-called critical universe or flat universe was very close to 1. It could have been 10, it could have been 0.1, but sort of geometrically, it was very close to 1. And that meant the universe has flat curvature, zero curvature. That means any triangle you make, no matter how big in space, I'm not talking about the surface of the Earth or the center of a black hole, but in large enough regions of space-time, any 3 stars, 3 galaxies, 3 clusters of galaxies, 3 spots on the cosmic microwave background, they'll make a triangle, as any 3 points do. And if you sum the interior angles of that triangle, you'll always get 180 degrees. And that, okay, fine. So that makes geometry easy, much easier, easier than doing any other type of geometry, but it's startling. It shouldn't be that way. If I told you I have a bag and it's filled with ping pong balls, and on the ping pong balls, I've written down all the different curvatures that the universe could have. It could have any degree of positive curvature, meaning it could be spherical, that the triangular angles would sum to greater than 180 degrees, or it could be hyperbolic and the triangular angles could sum to less than 180 degrees. This would mean that every ping pong ball would have the value of the radius of curvature, either positive or negative. And if you think about the real numbers, they're distributed from minus infinity to positive infinity. And there's only one very, very special and very round number that sits between positive infinity and negative infinity, and that's 0. So imagine you pick out of the ping pong ball bag the one ball out of a bi-infinite set, a dual infinite both directions, positive and negative. You pick out the 1 0 value? You got to be kidding me. I mean, that's greater than winning the lottery an infinite number of times. And yet, Dickey said that's basically the situation we're in. And so Alan Guth, hungry for food and a paycheck and to support his burgeoning family, said, I got to explain that. And one of the ways he thought could be explained is if the universe underwent a superluminal expansion of unimaginable degree at an extremely early point in its history, right after the Big Bang, that would do it. It would inflate the universe, much like inflating a balloon. A balloon might start off very small, but if you inflated it to infinite radius of curvature, that means it would be infinite in dimension and the direction. But that would mean it would be perfectly flat. Any triangle you made on it would be 180 degree sum. And that's sort of the motivation that he came up with. Now, he used a particle physics trick called a phase transition, which were very much in vogue in the 1970s when he was trafficking in these sort of ideals. But he was able to come up with a theory that would explain the existence of a flat universe based on very simple understanding of the behavior of curvature in an expanding universe when it expanded at an infinite rate, at a near infinite rate, at an extremely early time. It also solved some other problems. It had some problems with it. But as I like to say, the flaws lead to new laws. So, for example, Einstein believed in the steady state universe, the eternal universe. That model had many, many flaws when confronted with Hubble's data of the expanding universe, 1929, and Friedman model led to a prediction of what this would actually look like. Lemaitre came up with the concept of the Big Bang. And this led to really the shattering and the destruction, as an experimentalist should strive to do, of the prevailing scientific paradigm, which was a static eternal universe that everybody believed in for thousands of years, including Einstein. And then, and only then, could flaws start to emerge in the Big Bang model, one of which was, why is the universe flat? Why is it so uniform? Why is the universe beginning from an expanding configuration? None of those were explained by the Big Bang model. And to explain those features, the concept of inflation was an ancillary auxiliary hypothesis that we are still testing, but has made stunningly consistent predictions, with the one caveat that we haven't observed the true sine qua non, the thing that only inflation predicts, which is this background of gravitational waves. And that's the job of the Simons Observatory.
Now, how do you look for them? You know, the signs of the gravitational waves, presumably you're looking at the CMB and then looking for a pattern there?
So exactly, when the universe begins expanding at this superluminal rate, the reverberations in space-time are going to cause unavoidably gravitational waves. Gravitational radiation, if you think about it, is present when two enormous 30 solar mass black holes collide together. When that occurred, it produced enough gravitational radiation that even a billion years later, from a billion light years away, that signal was still detectable by Earthbound instrumentation. Now, that was only 10 years ago, 9 years ago with LIGO, the first detection. Now we're doing that every single day, probing out into the universe. But that's only for two 30 solar mass black holes. Okay, I'm joking when I say only. I mean, that's pretty huge. But imagine every single black hole in the entire universe. Imagine all the mass of the entire universe. And imagine it not colliding over a quarter of a second, as these black holes seem to do in LIGO's detection threshold window, but instead they're happening, the entire content of the universe's matter budget coming into existence, not in a quarter of a second, but in a trillionth of a trillionth of a trillionth of a second. Imagine how violent that would be. That creates a gas of gravitational waves, which suffuse the universe and goes out all throughout the universe. And they exist forever like photons. They don't have a lifetime. They're true forms of gravitational radiation that have no known lifetime and propagate across the entire universe because they have no mass. So these waves were present at the formation of the first atoms. The fusion of proton with electron made the first hydrogen atoms in the universe. That occurred 380,000 years after the Big Bang, when the universe was a billion times more dense than it is now. That density of the universe, all the plasma in the universe, the hydrogen atoms, electrons, and so forth, they were getting bombarded or perturbed by these waves of gravity at that time. And then when the universe cooled slightly, such that the electrons and protons were forever combined, then the photons that were jostling them about, keeping them ionized, were then free to percolate themselves and propagate unimpeded without any further scattering throughout the history of the expanding universe until they enter our telescope. So they will bear this very, very minuscule imprint, but detectable nonetheless, if and only if inflation took place. Because inflation is the only model of cosmogenesis that predicts the background of gravitational waves. What they do is that they squash and stretch space-time itself, inducing this peculiar pattern of polarization, it's hard to say fast, called B-mode or curl mode polarization. Effectively, you get these little whirls and whirlpools of the polarization vectors on the sky. And we can detect that. And like I said, we did detect in 2014. And it was unfortunately a combination of the dust that produces the same type of pattern, but not from the gravitational wave mechanism. It's an imposter that happens to produce the same signal we're looking for, but it's not the actual cause. It's not the cosmological event that's causing it. It's a local astronomical event in our own galaxy. And that's not representative of the Big Bang at all. So that's an unwanted nuisance signal that now we know about thanks to BICEP 2 and other experiments, and we can remove it, hopefully, by making multi-frequency measurements. So I told you about the 60,000 detectors, bigger than all the number of detectors ever deployed combined in this field, designed and built by Suzanne Staggs. Half of them are going into the Large Aperture Telescope that my colleague and friend Mark Devlin has led at UPenn. And these detectors will, when cooled, they're polarization sensitive. And they're made of superconductors, so they have a vast change in their resistivity as they are cooled or heated between their transition temperature. They go from zero resistance to a finite resistance. We can use that transition as a thermometer. They're at the focus of this huge telescope, and we use that combination when in combination with the fact that they're intrinsically polarized. The detectors themselves have polarization sensitive detection mechanisms, like a polarized sunglasses in front of each one. And that's what allows us to make these exquisite maps of the polarization that my colleagues are already doing. We already have some of these maps, and we can already start the search for these things very soon, looking for gravitational waves after we commission finally the quality of the instrument. So it's just basically in a quiescent mode, just observing every single day. That'll be a few more months before we're in that fully, just crushing out data. But that's the general picture of how we go about detecting these faint primordial gravitational waves that would be the harbinger not only of inflation. People forget about this, but there's no way that you can have inflation, according to most cosmologists, including Alan Guth and Andre Linde, who's a friend of mine, many-time guest on the show. There's no way you can have inflation unless you have a multiverse. So not only is the Simons Observatory going to be a gravitational wave detector, not only is it going to be an inflation detector, not only is it going to detect neutrinos masses, possibly axions, it's going to be a multiverse detector, potentially.
Why is that required specifically why does that imply a multiverse?
So when you and I were kids, the universe was all there is. But we kind of had a more limited conception of what the universe was. We thought of the universe as everything we can see, which is certainly true. That is a form of the universe, that which has had time to influence our intellects, our minds, to inform us with information. That's called the observable universe. But there's a greater universe than just that. There is, you will admit, a region of time and space that we can't see, that's hidden behind, as your podcast is called, an event horizon. And that would be potentially the Big Bang itself, where effectively you're at an infinite redshift, such that there's no information that can be propagating from either the core of a black hole or even within the event horizon. So let's go back to what the multiverse really could mean. According to my friend Max Tegmark, there's actually 4 different types of multiverses, and there are different levels of confidence in each one, but there's also different levels of hype, surrounding each one. And there's also, I would say, different levels of, controversy around each one. So the first one is that there are regions of our universe that, by virtue of its capacious size, just haven't had time for us to know about their presence. Just as I can go out into the Pacific Ocean in San Diego, out of the side of land, and I can know about a tsunami that takes place in South America somewhere, but even though I can't see it actually occurring with my eyes because of the propagation of water waves, we'll bring that information, but only much, much later. So that's kind of regions beyond our observable universe are not ruled out. Then there's another type of multiverse, which you may have encountered in quantum mechanics from the many worlds model, where at each instantaneous instant, to be redundant, the universal wave function is branching off at a tremendous rate of 10 to the 30th branches per second, according to Sean Carroll and others. And at each moment, every quantum process that can occur is occurring. So you're married to your high school sweetheart and you're divorced from her, and the different quantum branching points occur in different universes, and that's an honest to goodness multiverse. And then there's the multiverse of other universes with different physical laws. And I've made the case, and I haven't seen this anywhere else, not to toot my own horn, but there's no reason we should only restrict ourselves to different, constants. Like the speed of light is different in multiverse, 420 versus multiverse 69, to make Elon Musk happy. Hopefully he'll be tuning into this. But the laws of math and philosophy and the transitive property of addition and modus tollens they could be different in these other universes. And so there's many different things of what we mean by multiverse. In the context of the cosmological multiverse that the Simons Observatory could, in fact, give evidence for, that would be another universe with let's just be simplified and say it has the exact same properties, but it's located, say, a light year away from us, right? So to see it in a vast space, so you have to first think of the cosmos. I like to call it like this. The cosmos is the set of every single possible 4-dimensional point in other words, in space and time. So every possible event in the past and in the future, going to infinity in both directions. And then our universe it may have been infinite, but let's just say it began at a certain point. We call that time equals 0 for our universe. But there could be another universe which started before our universe, and it's literally another spherical volume of space-time where all those events could just possibly reach an observer at the center of that region. And we're going to bump into that universe next year, but we're going to have to wait a year for the information from that collision of our universe to enter our telescopes or to leave an observable imprint. That's one way we could detect the imprint. Because if think about 2 soap bubbles, when they join together, there's and now they're one big volume. There is a region where they combine that's circular. that's a one-dimensional circle, and that's the border of the boundary between the two collision sites. And on that circular strip, the properties of those two universes are identical because they're the same universe at that point. There's still different processes occurring in the inside of each other universe, including the existence of a cosmic microwave background inside that universe and a surface of hydrogen atoms inside that universe that it will then be identical to the circle that is present in our universe. So we see a certain circular pattern according to certain scientists that have made predictions about that. That's one way you could say it. But the other way to think about it is that inflation requires a quantum field to be present everywhere within it. And that quantum field in the case of the inflationary universe is called the inflaton. The inflaton is a property of four-dimensional space, the same way that the Higgs field is a property of our three-dimensional and four-dimensional space-time too within our universe. But the Higgs field could vary between multiverse, universe 1 and universe 2 in this concept, these two different bubbles within this infinite four-dimensional space-time. But the inflaton there's only one inflaton field that fills all of the four-dimensional space. It has fluctuations from universe to universe, from point to point inside of the multiverse. But inside of each universe, there's only one intrinsic field. The fluctuations of it result in differing values for the constants of nature, perhaps, but they also lead to bigger or smaller values of the gravitational wave background, because there's going to be more violent expansion in part of the universe that we can observe than in a different part of the universe. That will lead to more gravitational waves in one part versus another, and that will lead to a differing pattern as we would observe the cosmic microwave background's B-mode polarization. So the B-modes are a consequence of inflation, but inflation itself can't seem to occur without a multiverse also existing. There's no way to have it, and this is what Andre Linde called these, kind of island universes or baby universes that would set off and nucleate and possibly go into and out of existence, the same way that when you go up tonight on the roof of your house and look up at the stars, you don't know if they're still there or not. Proxima Centauri could have died 3 years ago and we wouldn't know about it for another year. So this is what makes it so fascinating to do this type of science, using the cosmic microwave background, not only to detect particles, the massive dark matter particles, the only dark matter particles we know about, the neutrinos, perhaps detect the mass of the unknown dark matter particles, axions, but also detect the properties of early space-time itself, including gravitational waves. This type of astronomy is unique. It can do essentially anything you can do, I can do better. We can even potentially, with the Large Aperture Telescope made by my friend, colleagues group, Mark Devlin at UPenn, we could detect Planet 9 with the Simons Observatory. So we're talking about doing large scales possible, the origin of the universe itself, down to clusters of galaxies, down to individual galaxies themselves, down to planets within our solar system, down to individual highly energetic stars and transient phenomena in our universe, in our galaxy and beyond, and then down to the subatomic neutrinos, axions, and eventually, perhaps the graviton, the unification of forces and fields long dreamt of by none other than the great Albert Einstein. So this is really the culmination of my career. I couldn't have a better team to work with and work for. And I'm just so excited that, the next time we speak, hopefully we'll have some real data to talk about, in addition to this tantalizing hint that I mentioned from the polar bear incarnation of the Simons array, which is leading us to suspect at least there might be something strange going on in that Crab Nebula that has been observed since the year 1054. So really, John, this is the most exciting time I've ever had in my life.
It is exciting. Now, Brian, I know you have a heart out today, so I would just say this. Come back sometime soon when more papers are out, more data, and then let's talk about the graviton.
I would love to. It's one of my favorite subjects. Imagine, I'll leave you with a puzzle. Imagine if the graviton exists, that means it's a quantum mechanical particle. Does that mean that it also would experience the double slit phenomenon? Think about that. That's a homework problem for you for the rest of the school year. Until we meet again.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.